in terms of the flows and minima of the empirical risk or loss of likelihood. Classical mechanics at some point gave way to thermodynamics. We extended our description to incorporate heat, sort of hidden degrees of freedom. And now it's no longer about the energy on its own, but it's about free energy, sort of modified energy that includes this trade-off between energy that you can measure and entropy. That's a kind of accounting for hidden energy that you can't measure directly. Similarly, on the deep learning side, singular learning theory goes beyond empirical risk minimization and says that for large learning machines, like neural networks, what's really going on is also a similar kind of hidden trade-off, not between, between loss and complexity that minimizes Bayesian-free energy. On thermodynamics, we went further, right? So we went beyond dynamics to develop this theory of statistical physics, where thermodynamics is just a theory of macroscopic phenomena. In statistical physics, we understand the microscopic origins of the macroscopic phenomena that we can measure in the lab. And so this gives us a principled set of tools and formalisms for probing internal structure in systems, microscopic structure in systems, from external macroscopic perturbations. And the hope here, especially the hope that we have for developmental interpretability and other applications of singular learning theory to interpretability, are to do the same for AI systems, to develop a suite of interpretability techniques that discover internal structure by probing them in a systematic and principled way. And finally, statistical physics begat condensed matter physics as one of the directions in which it's gone. At this point, physicists are very close in many cases to being able to not have to figure out what the properties of a system are after the fact, but they're able to go through this inverse process where they start with a specification and compile this into material. We're not there totally yet, but this is what condensed matter theory is starting to give us. And I think the hope for alignment here is that we can develop analogous kinds of techniques for programming goals and values explicitly into models, starting with a specification, figuring out how to compile this into a learning process that gives us an aligned superintelligence. Okay, so that's the analogy we're going to go through. I'm going to go through each of these steps in much more detail over the course of this talk. But at a high level, you can already understand the parallels that we're starting to see between physics and learning theory. And I want you to notice two main trends going on here. So first is the trend from descriptive accounts of nature to tools for intervening and controlling nature, right? Classical mechanics initially started as an attempt to describe the motions of stars, apples, celestial objects, and it eventually gave us ways to design new kinds of mechanical systems better. As we go down this list, it increasingly looks like developing tools that actually let us control the properties of nature. On the other hand, the kinds of research we do, it really starts with a very empirical focus, usually. This is true across a wide range of different fields. Initially, it's a lot of tinkering. Thermodynamics at the start was, people maybe, I don't want to say playing around with thermodynamic experiments in their labs, but it was a bit of play. They were taking around, figuring out what works. And eventually, this gives rise to a more principled approach to understanding what's going on here. This is because, at the start, you're trying to describe systems that have few, very isolated degrees of freedom, where the experiments are very cheap to run, and where your failure tolerance if an experiment goes wrong is very high. As you push further and further down this stack of technologies, you start to work with systems that have many more degrees of freedom that are highly interacting, where the experiments are much more expensive. You can only run a handful at a time. The search space is much larger and therefore harder to navigate, and failure tolerance becomes much more costly. So these are the kinds of trends I see as driving the shift from descriptions, empirical descriptions, to increasingly theoretically motivated controls. And I think just as this has inevitably arisen in the history of physics, we actually need something like this in order to guarantee safety in the case of AI. So let me highlight the kinds of problems in AI safety that I think require this more principled science that we could start to develop by taking our physics ideas and techniques and applying them to AI. So first is the problem of generalization, which I see as being about the question, how to learn algorithms enable models to generalize well, or conversely, to enableize them to generalize in ways not intended. I think this is the inverse question of the engineering discipline of interpretability. So really with interpretability, my aim is to be able to understand the structures inside of a model that enable a model's particular behaviors. Where does the generalization come from? I see interpretability as being about a kind of generalization accounting. Okay, so are a model's goals and values actually aligned with designers' intentions? These are questions about structure inside the model and how that interacts with its behavior. On the flip side, that structure has to come from somewhere, and that structure most directly comes from the training data. So there's another scientific question here, which is the question of learning, right? How does training data, whether it's alignment training data or pre-training data or some other kind of training data, give rise to the capabilities, goals, and values that a model acquires over the course of the training process? I see this as the inverse problem of alignment, right? With alignment, we want to know, in practice, how do we control the data distribution over training in order to steer models where we end up? In practice, alignment today looks like making interventions in training data and using that to steer the model in a new direction. Can we do this in a more principled way? And then, of course, the question is how to put this all together to develop a more rigorous science of AI safety. And the thesis here is going to be that, well, maybe, just maybe, this is another area where physicists have something to contribute. Um, Now, I know you have to be cautious with physicists because you already believe this. You're all arrogant physicists who go out in the world and seize new fields for themselves. But in this case, it might actually be true. Okay, so let's actually come back to this analogy between the development of physics and the development of learning theory and deep learning, and start to fill in the details. I'm going to use this as a chance to introduce you to some basics of learning theory, in particular singular learning theory, and also use this as a chance to present on some of the work that we've been doing over the past 2 years at Timaeus. Part one, empirical risk minimization as classical mechanics. Right, so what are our elementary objects of study here? I'm going to start at the very basics. In physics, we're often interested in particles, or maybe for a mechanical system, it's a set of simple machines. Those are the objects of study. In in the case of neural networks, maybe it's neurons. Maybe neuron isn't quite the right unit of study. Maybe it's some other thing, but it's parts of some neural network architecture I'm going to claim. So what's the state? Well, in the case uh, of physics, we can identify the state with uh, some vector values, in particular values of position and momenta for all of these different particles. For the case of neural networks, it's the weight configuration, right? The vector of parameters that identifies our model for a given architecture. And the state space is this nifty trick that we get from physics where we identify states a system can occupy with points, elements of some space. You know, with neural networks, there are different choices you can make, right? You can say, oh, it's weight space. Weights are the microstates in this case, or maybe it's functions themselves. And actually, the difference between these two perspectives is going to be central to singular learning theory in a moment when we get back to this. The evolution of these systems, well, in the case of physical systems, evolution is dictated by energy. Right? So for conservative systems, energy conservation of energy is the major constraint that determines the kinds of allowed dynamics a system can follow. And you have to satisfy Hamilton's equations. Is equivalent to saying that the Hamiltonian is this generator of time translation symmetry. On the in general though, often our systems, at least classical mechanical systems, aren't exactly conservative, right? They lose energy to their environment through friction, through heat, And so we actually describe them as dissipative systems, where a system slowly relaxes to some ground states, some minimum of this energy landscape. So evolution in both cases, whether you have a conservative system or a dissipative system, is determined by the energy. This is in many cases so obvious that it doesn't even bear mention. In the case of learning theory, the analogous quantity is the loss or the empirical risk, depending on how you talk about it. Maybe two approaches that sort of map onto the left two categories. On the one hand, you have Markov chain Monte Carlo sampling. So if you're trying to sample maybe at roughly a constant level set of loss, you use MCMC techniques. It's not actually conservative in practice. Even if you're using Hamiltonian Monte Carlo, which is explicitly modeled after the physical system because of discretization error and these kinds of things. But that's one way to view what's going on in a Bayesian setting. Or on the other side, the thing that we're usually doing in practice is we're using stochastic optimization. So SGD, Atom, Yuan, any kinds of these optimizers, where we're taking one step at a time downhill towards minima of the loss. So there again is very clearly it's the loss that determines evolution, in particular the gradient of the loss that determines evolution. And if you start with the end point of this as your definition of learning, you get what's called empirical risk minimization. This is the dominant or the main paradigm in classical learning theory. So the empirical risk is this quantity R sub n, which is defined as the average loss over your data set. So there's a useful distinction that learning theorists make between the loss function, which assigns a penalty to individual samples, and the empirical risk, which is the aggregate quantity. Often you'll hear loss being used synonymously for both empirical risk and this loss function. At times it's helpful to divide the two. So empirical risk minimization is the branch of learning theory that studies properties of minima of an empirical risk. How close is this to the true population risk? If I were to do this for many different data sets, how far apart are those? How close am I actually able to get to this optimal empirical risk minimization procedure using a given stochastic optimizer in practice? These are the kinds of questions that learning theorists study. But anyway, in both physics and learning theory, it's the energy or the loss that determines the evolution of the system. In particular, there's this idea from dynamical systems theory that it's the geometry of the potential, so it's the geometry of the energy landscape or of the loss landscape that determines the qualitative shape of dynamics of trajectories over those phase spaces. And in particular, the local geometry around the vicinity of critical points. If you want to understand the qualitative dynamics that a certain physical system allows, it often suffices to just identify where the critical points are, to do a local second order expansion around them, understand are these stable points, are they repulsive critical points, to plot a few lines like this. And now you understand up to some invertible diffeomorphism, what is actually the shape of dynamics you care about. Okay, so we're seeing some analogies between empirical risk minimization and classical mechanics. They study different objects, but we represent state in a very similar way. The evolution is given by similar quantities, similar objects. There's a difference here in that, um, in the case of physics, we're interested in symplectic geometry, which is not the case usually in the case of learning theory. But on the whole, we can squint and say that the physics, the physical energy, and the loss in a learning theory setting are really sort of the same object. And in both cases, we're interested in the role of geometry of this landscape of losses, this landscape of energies. That brings us to step 2 in this process from classical mechanics all the way down to condensed matter theory, singular learning theory as thermodynamics. Okay, so the key change that we're going to need to make in order to go from classical mechanics to thermodynamics, from empirical risk minimization to singular learning theory, is we're going to consider some sort of asymptotic limit, a thermodynamic limit, which is usually defined as taking the number of objects to infinity, taking the number of degrees of freedom thereby to go to infinity. In the case of learning theory, we're interested in really two limits, which are sort of both going on at the same time. The limit of the number of dimensions, the size of your model getting larger and larger, and the number of samples getting larger and larger. Now, the second limit I won't really talk about here today, but it is also a very interesting limit to study. Okay, so what happens when you take these limits to your physical systems? Well, one thing that happens is that your description of the system is no longer going to be deterministic and pointwise, but it's going to become probabilistic. Because for thermodynamic systems, where you have many, many particles, you can't know all of the positions and momenta of all the particles. It's completely impossible. Moreover, even if you did have some way to determine them, um, even if you did have some way to, given an observation of those values, if you were able to calculate what the values will be in the next time step, you have some infinitely large computer, you have uncertainty about the initial conditions. So this uncertainty means that we're going to take a kind of probabilistic approach and describe the density over possible states rather than the evolution, a trajectory of a single state. Now, similarly, we're going to take a similar kind of change on the learning theory side. So instead of talking about stochastic optimization, let's talk about Bayesian inference, or the evolution of a Gibbs measure. Now, on the physics side, we end up with the following description of the distribution of possibilities given by the Boltzmann distribution. So we fix a set of observations. Maybe we measure something like the number of particles, or the allowed volume, or the temperature. Like we allow the system to exchange heat with the environment, but we know what the temperature is externally, what energy is the system going to rise to. So using this constraint optimization process where we maximize uncertainty subject to the constraints we'd like to enforce, that the energy of the system, the average energy, is equal to the energy that we actually observe or measure, we end up with a Boltzmann distribution. This is the unique entropy maximizing solution for the distribution over states subject to the constraint that we want the average energy to be what we observe and that it's a probability distribution. Similarly, what if we wanted to apply the same idea to the learning theory context? So we start with empirical risk minimization, and now we say that we're uncertain, right? We don't actually end up with an optimal choice of weights. We end up with some choice of weights that has some average loss, some average empirical risk. If you solve the same constraint optimization problem, then you end up with a similar looking Boltzmann distribution, where now the thing in the quantity, the probability of a given state I, is going to be equal to the empirical risk of that state in this Boltzmann form. And so that's, if you squint at that thing, that looks a lot like, well, what we get from Bayesian inference. So Bayesian inference is usually written out this way. So the posterior, the probability of some weights given a data set of n samples, is equal to the likelihood of that data set for a given choice of weights times some prior over the marginal likelihood. This is a normalizing constant. But you can rewrite this in a way that looks more familiar to physicists. This is rewriting it in the Boltzmann form that we saw from this max-end derivation. So here, now instead of using this R notation, we're using a negative log likelihood in the exponent. So this is a more restrictive form of empirical risk, where the empirical risk, where the loss function is precisely a negative log of some model probability, and this z sub n is really just a different way of writing the probability of the data set, the marginal likelihood, the normalizing constant. Okay, so this is the sense in which you really can say that Bayesian inference is just statistical physics, where the Hamiltonian is given by a negative log likelihood, which is a random variable as a function of this data set. And that brings us back to this prediction. So, the limits of a process like SGD are not necessarily going to be something that is well modeled by a Bayesian posterior. This is an open question. We don't know. But at least we can take a sort of physics-inspired maximum uncertainty approach when trying to describe the kinds of end states we might end up with from some physical learning process, and use that to end up at Bayesian inference as our starting point for physical description. In many cases, it's possible to go the other way. So we have this density-based view, and now you end up with a trajectory perspective, or at least a pointwise perspective. And in the physics case, this looks like taking some kind of low temperature expansion, where as you lower the temperature, all of the probability mass is going to concentrate around the ground states, the lowest energy states. In the case of Bayesian inference, that looks like taking a large data set expansion. As you sample more and more data, you're going to get more and more confident about the optimal choice of weights. So in general, you'd think that the probability mass will just concentrate around the true weights, the optimal choice of weights. As it'll turn out, this gets a little more complicated for singular models, which is why we need singular learning theory, but it's a useful starting intuition for what happens. And to see this, let me reintroduce Bayesian inference, not in terms of this maximum likelihood derivation, maximum entropy derivation, but on its own conventional terms that is introduced. I'll explain why the number of data points is analogous to temperature in a moment. I'll show you. So, okay, in a Bayesian inference setting, we start with a space of hypotheses. We're going a step up in abstraction. So we have some space of hypotheses, and we have a prior distribution of beliefs over this space of hypotheses. And we'd like to update this space of beliefs after we see some data given from this data set N, where each of these samples is drawn from some distribution, which we'll call the true data generating distribution. And the way we do this update is through a likelihood, which is this product of probabilities assigned to each sample by a model for a given choice of hypothesis. So this Bayes rule, and the first modification we have to make to actually get to something a little more practical is to move to a parametrized setting. So instead of abstract hypotheses, you identify hypotheses with some real valued vector of numbers. This is easier to do some kind of search over. The second thing we do is we lift the, as before, the likelihood into the exponent. And so here you see that n plays the role of a beta, of an inverse temperature in the case of physics. Okay, so then again, what I said before is that we saw how you could go from this sort of trajectory-based view to a density-based view if you assert uncertainty and you solve the solution subject to maximizing uncertainty, maximizing entropy. And now we're going backwards from a density-based view to this pointwise view. If you sample more and more data, then naively you expect at some point your posterior will just concentrate like some delta function around the optimal hypothesis. And so learning for a Bayesian learner reduces back to empirical risk minimization. Hopefully. But again, with this major caveat. So okay, so what is that caveat? How do we address this? Well, we'll see in a second what that looks like. Now the important consequence of taking this probabilistic perspective is that really the key quantity that controls the evolution of our system is no longer the energy itself, no longer the energy on its own, but a modified energy. It's this free energy. The exact form of that free energy is going to depend on the physical setup you have, so the walls of your system, as we'll see in a moment, and those will give rise to different kinds of free energy. But now this is the actual quantity that you're trying to minimize, and it's a minima of this free energy that describe the physical states that you expect to actually observe. Similarly, in the learning theory case, we end up with a Bayesian free energy. This is different from the variational free energy, so if you've heard of that, just put it out of your mind and don't think about it anymore. This free energy has this form. For regular models, it looks like the number of samples times the negative log likelihood, plus number of parameters divided by 2 times a log in the number of samples, plus some, this should be an order constant term. The second term down here is for singular models, where we see the only difference is that the second term has turned from a d over 2 into a lambda. And we'll explain what that means in a second. Okay, but the important thing from this slide is that we're no longer trying to minimize energy directly. We're now minimizing this free energy. Minimizing the free energy in the case of thermodynamic systems requires trading off these terms that show up in the expression for the free energy against each other. Similarly, minimizing the free energy is going to involve trading off these terms against each other. So we end up with a kind of implicit regularizer, where the thing you're actually minimizing is not the loss itself, but this modified loss. Okay, so coming back to Bayes' rule, it turns out there's really two sides to Bayes' rule. There are really sort of two kinds of learning hidden away in this. So we talked about Bayesian inference. That's just the shape of the posterior is finding the right weights for a given data set. But there's this higher level problem of finding the right model class, the right architecture for the problem at hand. Because there's this implicit dependence on the architecture of your problem when you're solving Bayes' rule. Yeah, I think I'll answer that question in a little bit. Okay, so two sides to Bayes' rule: Bayesian inference, model class, selection. For model selection, you can just set up a new Bayesian learning process or Bayesian inference problem, where now you're doing inference over hypotheses where the hypothesis is an entire model class rather than a specific choice of weights. This is going to give you some sort of turtles all the way down kind of hierarchy of Bayesian updates, a meta Bayesian update. Well, as before, you can consider what happens when you sample lots and lots of data. In that case, this meta Bayesian inference problem reduces to minimizing not a loss, not doing empirical risk minimization, but doing free energy minimization. So the basis for finding the right model class in practice in empirical settings is to do these is to do free energy minimization, where free energy is the negative log of this marginal likelihood, the denominator from Bayes' rule. So for regular models, as we saw, this reduces to basically just minimizing the loss, because the second term in the expansion of the free energy was a term that depends on the number of parameters divided by 2. And that's just, if you have a bunch of different architectures that have the same number of dimensions, they're going to say that you should just pick the architecture that has the highest loss. And this particular approximation of the free energy is known as the Bayesian information criterion. Okay, so we're minimizing not the energy, not the loss, but this modified energy or loss. And that involves playing these terms off against each other. Yeah, I'll share these slides after. Okay, now we move on to talk about invariances. So in physical systems, we have this set of invariances that comes from symmetries. I can rotate my description, my frame that I'm measuring a system from, and that shouldn't actually change any of the properties of my system because the system is somehow more fundamental than where I'm measuring it from. In the case of neural networks, there are also these kinds of invariances, but in many cases, they're actually more interesting than the invariances, the symmetries you see in the case of neural networks, in the case of physical systems. There's just many more of them. And the more interesting thing is that the set of symmetries, the set of degeneracies, varies from region to region in parameter space. So really, this entire set of pictures is only for the learning theory case. So real-world networks, real-world learning machines like neural networks tend to be singular. That means one of two things: either the minima are non-isolated, or you have some points that have a non-invertible Hessian. And that means that Unlike in physical systems, the ground states don't locally look like a harmonic oscillator. You need higher order terms in your Taylor approximation in order to faithfully capture this. And as a result, because a lot of the classical theory assumes that models are regular, the resulting derivations don't hold for neural networks. You have to do something more sophisticated. Okay, so as we saw, what you're actually minimizing is this free energy that requires trading off a term that shows accuracy against complexity. For singular models, the second term is variable. It's not equal to some fixed number of parameters divided by 2 value, but it's got this lambda term, this learning coefficient term that can vary. Because the trade-off depends on the number of samples, you can see, as we'll see, the trade-off can jump suddenly as you sample more and more data. Eventually, the linear term is going to dominate the logarithmic term. So as you sample more and more data, what you should expect is that the loss will continue to go down as the complexity goes up. You'll come to favor more complicated solutions that fit the data better. So really what's going on implicitly inside of Bayesian models is an implicit form of Occam's razor. Models find the optimal trade-off of complexity against accuracy for a given set of data, for a given data set size. Yeah. And this is what's really unique about singular models. For regular models, all of the geometry all over the loss landscape. Yeah, let me go back to this. So models favor the higher the lambda value is, the more complex the model is. So you want to minimize the free energy. You have two ways to minimize the free energy. You can either minimize the loss, try to get a more accurate model, or you can minimize the complexity and end up with a simpler model. And so the exact way that you're going to find a way to satisfy this trade-off depends on the number of samples that changes the coefficients. So singular models are special because unlike regular models, the complexity varies from region to region in parameter space. Non-singular models are kind of boring. All of the models inside of a regular model, all of the regions of weight space look sort of the same and have the same complexity. And it's because of this flexibility that models are able to learn such a wide range of different kinds of algorithms. So really what we end up with are maybe 3 forms of learning. Inference, finding the right weights; model selection, finding the right model class; and this internal form of model selection that's actually automatically done when you're doing inference inside of a singular model. Yeah, okay. Okay. So this is where we start to pull in more of our physics knowledge. One of the interesting things we know from thermodynamics is that systems can undergo phase transitions. If you change, let's say, we'll call it a hyperparameter, some control lever, maybe the temperature or the pressure, then you can suddenly change the free energy trade-off to favor a different state of matter. So here I've got a simplified toy model of the phase space of water, and I've illustrated a first and second order transition, where we see the free energy landscape initially favors one kind of solution, and then at some point as you move along this direction at constant pressure and in increasing temperature, you'll cross this line. You'll see a phase transition where the minimum jumps to some other kind of solution, and you expect to see your physical system jump from a liquid state into a solid state or a gaseous state in this case. So there are different kinds of phase transitions you encounter in the case of physical systems. From this free energy formula that we just saw for neural networks, we immediately predict that there are first order transitions for Bayesian learners. So again, look at the free energy trade-off between loss and complexity. If you have two regions of parameter space, where region 1, region 2, the loss on region 1 is higher, so region 1 is less accurate, so it's a worse fit of the data, but region 1 is simpler, it's less complex than region 2, then if you plot the free energy of these two different regions as a function of the number of samples, you see a transition where initially the region that minimizes the free energy will be phase one. At some point, it'll jump to being phase two. We get a first order transition between the two. And so what we have here is a little phase transition in the inverse temperature parameter. Now, I'll flag one distinction with the classic thermodynamics presentation of phase transitions, which is that usually when people are talking about thermodynamics, they're thinking of an asymptotic limit where you take the number of samples, the number of particles to infinity. If you do this, then you get a discontinuity. You get a non-analytic change in the minimum. For neural networks, where the number of parameters is still finite, and the number of samples in this case also still finite, that doesn't actually happen. So there is a smoother change between the two things. There's no discontinuous jump. However, in my perspective, the key feature of a phase transition is not actually the discontinuity, it's the exchange of minima of the free energy, the change of the structure of minima of free energy. And that's the thing that we see here. Okay, so, are these phase transitions actually real? Do they actually occur in real systems? The answer seems to be a definitive yes. On the left-hand side, I've plotted for deep linear networks trained with SGD. And on the right-hand side, I've plotted the evolution of a toy model of superposition, again trained with SGD. So now we're going back from this formal framework of Bayesian inference to study real-world systems trained through this other stochastic optimization process. We're asking the question, does this theory actually predict the kinds of phenomena you observe in practice? I've got a nice little animation where this toy model of superposition goes through one jump in which the complexity in green jumps up in a styrose fashion, and the loss goes down in blue, and then it goes through another transition as it settles into its final form. It's a representation of the latent weights. And again, the complexity jumps up and the loss goes down. So using this theory, you can actually predict the set of allowed transitions in these systems. You can do this at a larger scale as well. So we recently put out a paper where we investigated a set of transformers trained to do an in-context linear regression task. So what you find here is that you can use the same free energy formula trade-off to predict which algorithms models learn as a function of training time and as a function of a changing data distribution. You train a bunch of different models and different data distributions. Where do you end up? And how does that change over the course of training? You absorb this for a second. It's not important to get all the details of what's going on here. Yeah, we'll get into constraints, enforcing constraints later. Okay. Oops, I clicked it away. Okay, these are still kind of toy systems, or at least artificial systems. Do they actually also occur in real models trained on real data? There, the answer also seems to be yes. So this is still for a very small set of 3 million parameter language models. But what you find here is that models learn in a succession of stages. They first learn bigrams, then they learn n-grams and skip n-grams. Then they form the induction circuit in two parts, overlapping parts, and then finally they converge. In subsequent work, we found that there are other things going on here. So the models are also learning decads and forming this other circuit. But what you see, the most important thing is that in the loss decreases pretty smoothly throughout the entire training process. However, if you also track this learning coefficient over time, quantity you can estimate, then you find these plateaus. And these plateaus actually correspond to when these stages that you can classify using conventional mechanistic interpretability techniques end. So looking at the geometry, using this theory from SLT, we can automatically identify developmental stages, which then after the fact turn out to be interpretable. Okay, so that's still for quite small models. In the meantime, we've been looking at larger and larger systems, and there'll be work coming out in the next few months or even sooner on scaling these techniques to larger models, 10 billion parameter models. Let's get back to the analogy. Okay, so we've gone already through a lot of content. See, there's a question about Yeah, so something I swept under the rug is what is the link between training time and the I need to plug in my computer. What is the link between temperature in the Bayesian setting and training time in the SGD setting? And sort of making this comparison requires requires assuming that there's some sort of link between the two. Now, what exactly that link is, I don't know. It's an open question. But at least empirically, assuming that maybe an increase in training time is sort of monotonic in the effective number of samples that the equivalent Bayesian learner would have seen is a reasonable assumption. But yeah, these are open areas of research. If somebody in the audience solves this, makes progress on this, I would be very happy. And then there's a question of how glassy are these landscapes. Yeah, so it's again, I'd say this is an open question that if there are glass physicists in the audience, you should study. Um, One thing I think tends to be ignored in glass physics, although I'm not very sure about this, is usually the focus I think is on non-convexity of the landscape, and this the idea that there's many different local minima, many different points. And the kind of key idea that we're getting from SLT that is that it's not just non-convexity. It's also degeneracy. It's also the fact that you can continuously change weights locally without necessarily changing the loss. Okay, but with that, we're going to get back into the talk. So we saw this link between classical mechanics and empirical risk minimization, energy and loss. Then we move to thermodynamics, where it's no longer about energy directly, but free energy, uh, thermodynamic free energy and Bayesian free energy. This predicts phase transitions that you actually observe in real systems, including neural networks trained on language data. What other consequences do we get from changing to this thermodynamic kind of perspective? Well, one thing that changes is we're no longer necessarily interested in the particular value of loss at a specific choice of weights. We're more interested in the expectation of energy or the expectation value of loss over some region of parameters. So in the case of SGD, you can imagine integrating over all possible weight initializations, or marginalizing over all possible realizations of the batch schedule. Okay, so the kinds of expectation values that we're interested in on the physics side are things like energy, volume, particle count, right? Depending on the ensemble you've chosen, maybe it's temperature, pressure, chemical potential, things like heat capacity, conductivity, uh, the magnetization, a bunch of these quantities. On the learning theory side, it's typically things like generalization error. What's the expected loss? Not on the data set that I trained on, but if I were to sample new data, what kind of loss should I expect it to see? And can I predict what the yeah like where do I get this from in the theory? So the answer will be this learning coefficient quantity, this measure of complexity that we saw earlier. Okay, coming back to the free energy formula one more time. Maybe if I'm being a little bit implicit about it, but I think this is a very important formula that is worth committing to memory. Um, what we see here is this trade-off between loss and complexity, and this quantity is the learning coefficient or the complexity. So what else is it? So far, I've only introduced it as a coefficient that shows up in this formula. Does it have any definitions on its own terms? So I want you to think of it as having two sides. On the one side, it's a measure of geometry. It's a measure of the amount of degeneracy in the loss landscape. On the other hand, it's a measure really of algorithmic properties, a measure of model complexity. Get back to them in a second. So let's take the geometric side first. So the learning coefficient measures the volume scaling rate. Consider some loss landscape, which I've depicted on the left-hand side. You're going to choose a choice of weights, a minimum, a local minimum, and ask, how much would my loss change under a local perturbation, under a typical local perturbation? what's the amount of volume below a tolerance epsilon? In this case, what's the area of the blue region? The volume for a given tolerance epsilon scales in general like some constant times the height epsilon to the power lambda, where this exponent is this volume scaling rate, this learning coefficient. Let me give you a few examples. If you have a paraboloid, the learning coefficient will be maximal. This will be equal to the number of dimensions divided by 2. But if you have something more interesting like this quartic thing, then the learning coefficient can be smaller. In this case, it'll be a half. Maybe something even more interesting like this normal crossing thing, then you get the learning coefficient is equal to 1/4. Okay, so importantly, I want you to notice that at the origin of these bottom two examples, the Hessian is the zeros matrix. So local second order information can't distinguish the geometries of these bottom two examples. Moreover, when people usually talk about flatness or base and broadness, they're talking about properties of the Hessian. But from this volume scaling formula, you actually see that the dominant contribution to volume doesn't come from curvature. It comes from degeneracy. It comes from this learning coefficient. The learning coefficient measures exactly, how far away from being well modeled as a local harmonic oscillator am I? How far away from the second order approximation am I? And you can estimate this, right? So this is the formula we use to estimate this in practice. We just look at for a given choice of weights W star, how much does the loss increase from that value to points in the neighborhood? You sample a bunch of points nearby, you take the average over those points, and you measure that increase. So this lambda is associated to a particular triplet of things. It's associated to um, a choice of distribution that's generating the data. It's associated to the model, your architecture, and it's associated to the prior, although the effect of the prior is vanishing under reasonable assumptions. So it depends on data, and it depends on your model architecture. If you change the model architecture, then yeah, in general, it could change. Although you might expect some kind of universality where the complexity might be, if you have sufficient amount of expressivity, maybe the complexity won't change anymore if you increase the model size or something like this. Okay, so I said it has this two sides, geometric degeneracy and model complexity. So let's focus on the second option. So for non-singular models, regular models, as we saw, the learning coefficient is just equal to the number of parameters divided by 2. If it's the case that a given parameter doesn't contribute at all to your model, then the learning coefficient acts like an effective dimensionality, right? It's going to be a half smaller because it doesn't get any contribution from this direction. In general, though, you can have these more complicated geometries that have beyond second order contributions, and then the learning coefficient can be an arbitrary rational number. So it's going to be something that's a bit richer than just an effective dimensionality. This is the sense in which we see it as tracking complexity of the model. Something that is very closely related. In fact, it is the dominant term in the description length. It determines the description length of these models. To give you a few examples of what this quantity looks like in practice, what degeneracy looks like in practice, consider deep linear networks, where you have the truth is some linear transformation of data, and you have a product of matrices generating is your model. What happens in this case is that the expressivity of your model, isn't any more than if you had just a single matrix here. But it turns out that depending on the rank of the true matrix, you might have more or fewer free parameters inside of your model. Right? If you're implementing this 1, 0, 0, 0 matrix, then you gain these free parameters in the B matrix. Okay, so here we see an intuitive notion of lower rank means more degeneracy, means lower complexity. I'm going to jump over this for the sake of time, but a dead neuron would be another example where you gain free parameters If you are always activating a ReLU neuron, then it's going to be simpler. So these are all cases where we're starting to see some link between the learning coefficient and complexity, algorithmic complexity. And perhaps the most important part of this is that the learning coefficient determines generalization error in the Bayesian setting. So the key quantity for Bayes, for Bayesian inference, is the Bayes generalization error, the KL divergence between your true distribution, what's called the posterior predictive distribution. This is the predictions you would make if you were using your entire posterior. And it's the expansion of this Bayesian generalization error. The first term is the learning coefficient divided by the number of samples. So if you have a larger data set, you have better generalization. Or if your model is simpler, you get better generalization. And this is essentially why classical learning theory was so wrong about neural networks. They predicted it would overfit precisely because they predicted generalization is proportional to the number of dimensions, when in fact, it depends on this often much lower model complexity. So how do you control these systems? Well, in the case of neural networks, you use walls. In the case of physical systems, you use walls. In the case of neural networks, you use data. Right? So this is true for basically all the techniques we have to control neural networks. Whether you're doing capabilities and you're training next token prediction on internet data, or you're doing some instruction or safety fine-tuning, whether you're using RL to train chain of thought, or using RL to, instill your preferences via some learned reward model, or if you're using some kind of sophisticated training data curation loop, or training your model to modify its own outputs based on a constitution or some specification, as in deliberative alignment. So all of the techniques we have for steering models, both capabilities and alignment, look like changing the walls of your system, which means changing the data. This is how we constrain them. With an eye to the time, Archana, can I go over 15 minutes?
Yeah, I think we can do maybe 10 if that is okay.
Okay. Okay, then I'll do
Yes.
that. Okay, so coming back to the link again, on the physics side, we have all these different, the thing that characterizes thermodynamic systems is no longer the properties of individual systems, but it's these relationships between our observable parameters, the relationships between changes in walls and what you observe the system satisfying. So these are captured in the ideal gas law. And similarly, the last decade of deep learning has been characterized by the very same principle, which is scaling laws relating compute, dataset size, parameter count, and now increasingly test time compute and model properties. Yeah. And maybe the risks from these different very different fields also are similar. But I'm going to let you deliberate on that on your own time. So we went through a lot in the link between singular learning theory and thermodynamics, and I'm really just going to take these last 10 minutes to show you a little bit more about where this is all headed and what it could be in the future. Okay, so now we're trying to go from thermodynamics to statistical physics. So statistical physics, we introduce a richer set of response functions, a richer set of observables. We're not just measuring things like average energy, but we want to understand, how does my energy respond to a change in temperature or some change in external perturbation? And this gives us this set of susceptibilities, correlation functions, a bunch of other things. On the learning theory side, we can do the exact same thing. So this is what we did in a recent paper. We just took the definition of susceptibilities from physics, which is a derivative of some observable, like the expected generalization error, and use this to measure for a given part of the model, how much does it contribute to predictions on some data set. Okay, so let me just go back to this again. So we're perturbing the training data. We might do something like upweight GitHub data and downweight wiki text and ask, how does this change the expected generalization of my model on some other data set? And you can quantify this using the susceptibility that you can actually estimate. So what you're starting to see here is a correspondence between sensitivity and weights, right? How much does the loss increase under change in weights? And sensitivity in data. So how much would the loss increase if I change the data distribution? So what we see in SLT is that these questions are very closely linked, and this gives us a handle on interpretability, um, that gives us the information about interpretability we want for generalization. So we saw the in distribution solution was given by this Bayes generalization error that tells you how much would the loss change in average for data that's sampled from the same distribution. And using these susceptibilities, we get the first order linear correction to this quantity if we try to execute some sort of distribution shift. So you can imagine doing the thing that physicists always do, which is just continue this expansion, and study how many terms in this expansion do you need in order to faithfully model the effect of some distribution shift on my expected generalization. This gives us a local way to handle the question of trying to get it out of distribution generalization. How do we probe these systems in practice? Well, in physics, we have spectroscopes. We have a bunch of tools that apply some kind of perturbation to my system or decompose it in some way and then look at patterns in that data. Well, in the case of neural networks, we're using stochastic gradient MCMC techniques. You really can just use SGD, add a little bit of Gaussian noise, alternate these steps, and use that to sample the local geometry. And then from that local geometry, compile these estimates, like the learning coefficient we saw. And this works at scale in practice. And for some cases where we know the ground truth, we can actually measure it accurately. Okay. So how do we actually get at measuring internal microscopic structure using this technique? Right? Statistical physics, at least the way I'm defining it, goes beyond thermodynamics in that it actually tells us the microscopic origins of macroscopic behavior. And so what structure means in physics typically means patterns in these response functions. If I apply systematic perturbations of many different kinds, what patterns do I observe in my matrix of input perturbation, output response? And you can do something exactly analogous in the case of neural networks. So let me define this. So we have this susceptibility, which is associated to a particular component and a particular choice of data. And that's what I've put in this matrix. Now, the kind of thing I can do is I can just take PCA of this data. I can look at the linear algebraic structure inside of this matrix. What you end up finding is that you actually recover precisely the known structures in this model. This figure is actually out of date, but no, never mind. It's up to date. What you find is that the first PC2 distinguishes the heads involved in the induction circuit from heads that are not involved in the induction circuit. The second component distinguishes particular kinds of heads within the induction circuit from other kinds of heads. So you're starting to see a way to use patterns in this response function, in this response matrix, to do automated circuit discovery. And this recovers everything we knew about this model previously, as well as revealing some additional new things that we didn't know beforehand. Okay, so yeah, I'm gonna move through the rest rather quickly. At the high level, where we're trying to go is with this link is to develop more and more nuanced, high resolution observables of geometry and use these statistics to infer algorithmic properties of our models. This is the basis for using the same kinds of formulas as in physics to understand structure inside of neural networks. Maybe the problems again are very similar. Okay, so I'm going to close on basically just this slide, which is my hope for what we could do in the future. Right? In physics, we've gone from this descriptive account to something that's more like prescription. In some cases, we can do sort of systematic digital screening of simulations to automatically find materials that exhibit a property we want them to have. if these simulations are faithful enough and modeled in a suitable way, then you can actually optimize directly over them. And so you can use our physical understanding now to program materials that have the electromagnetic properties we want, specific kinds of band gaps, and all the other kinds of physical properties we care about in physical systems. Maybe we can do similar things on the learning theory side. Maybe we can develop automated tools for eliciting behavior from them. Maybe we can develop automated tools for filtering data, for designing the curriculum of training data to steer the learning process where we want it. Maybe we can develop the analog of lithography. So we're not uniformly imbuing a physical system with all the same properties everywhere, but we're able to localize capabilities or values to some particular part of the model. Really, the dream here is, on the physics side, and this is an open question, is to develop a materials compiler. You start with a specification, you turn it into material. Or more particularly, you start with a specification, and you turn it into a construction process, some kind of recommendation and ingredients list, along with a set of instructions for how to combine those ingredients in the right order. Maybe we can do the same for alignment. Maybe we can start with specifications instead of this ad hoc process we use to design models nowadays, and compile our specifications into the training data we need, the ingredients, and the particular order we want to train them in. If you have more questions, then talk to me after. We've got a lot more that I can share, another talk or two that goes into more detail. It's safe to say that the links between physics and deep learning are many, and they go very deep. And well, there's work to be done. So I'll close off on this slide, where I think many of the fundamental questions we care about in safety are really questions about developing a better scientific understanding of these systems and turning that scientific understanding into tools that we can use to steer them more reliably. Thank you.
Yeah, awesome. Thank you so much, Jesse. I know it was it was a really good presentation, especially with, I think you had minimal text, but it was very impactful. So yeah, thank you so much for putting it together. I think we have a few questions from the
Okay.
audience. So should we start
So
from
maybe we
questions
can,
that were a bit
yeah.
earlier?
Yeah, I think I've responded to most questions as they've come along. I'm going to
Okay.
respond to Paul's. So, yeah, maybe part of the problem is actually identifying safe quantitatively enough to be able to actually use this to learn, I guess. Yes, I agree. This could be a real gap. Um, Maybe one hope is that currently, we optimize against one objective function, and we try to minimize this one objective function, and that can lead to problems. So we saw this with sycophancy, right? The recent example where OpenAI had this drama about their model being way too sycophantic, they claim was because of the way they combined several different objective functions in their reward model, which led to one reward signal being totally overrepresented compared to the other things, and that reward signal selected for sycophantic behavior. So maybe just having the ability to set more explicit constraints about downstream behavior instead of compiling them, stitching them together in this ad hoc way, and really doing constraint multi-objective optimization would give us a handle here. There are already ideas for doing this kind of thing. I'd say within the conventional ML field, but I think there are probably ways to do this better.
Awesome. I think, is it Dennis?
Yes.
Uh,
Hello.
yeah.
Hello, Jesse. Really great talk. Liked it. So I have a question that I actually posted, but I will reiterate. So
Mhm.
it seems that currently SLT is mostly centered on developmental interpretability, connecting data to the loss landscape and parameter landscape. However, my question is, can the same be applied to in-context learning? Because we
Mm.
know that transformers in particular
Mhm.
as they grow the context, they essentially adjust their internal representations, and they are making decisions. They are kind of choosing in which hypothesis to unravel, which to inhibit. And this is important to kind of explore the space of possibilities. So my question was maybe a little bit arbitrary. It's just one way how this can be explored. It's a question about connecting the landscape of parameters and the landscape of activations, because it seems that while in parameters we may want to localize ourselves in this flat minima with relatively easy, not very complex structure, but in activation space we often want to actually be at a saddle point to make a decision, to be sensitive.
Yep. I think it's a great question. This is an open question. So I have a list of SLT open problems in SLT for AI safety that I'll share here. And one of them is specifically this question: what is the link between geometry and weight space and geometry and activation space? Now I link there some work that you could look at if you want to make a start on this. I think maybe the simplex folks also have some ideas here. See Paul's in the audience. Hi, Paul. The answer is I'm not sure about the specific in-context learning example. I expect that if the model is doing a very sophisticated form of in-context learning, that it's doing a singular form of in-context learning, right? It's actually forming algorithms on the fly and using those. Our collaborator, Susan Wei, has been thinking about this. I don't know what the current status of that is, but should be someone to talk to about this.
Okay, great, thank you. And just very quickly, I just have to ask this. There is also this kind of a little bit hyped, maybe in some area, approach with essentially considering piecewise linear regions and Voronoi diagrams. Yeah. I actually, for some reason, am forgetting how it's called, even though I am quite familiar. So I guess you recognize what I mean. Is there some people who try to see how this relates to singular learning theory, maybe?
I don't think anybody's tried that yet. So I think another great project that somebody could work on. So I think some of the works, the words you're looking at, like the polytope lens, is that what you're talking about?
Yeah, like it's spline cam. It's spline theory of neural networks, I guess it's called.
Yeah. That's interesting.
Yeah.
I think SLT would have something to say about why, in practice, the number of linear regions is often exponentially smaller than the total number that could be expressed. So that's linked to degeneracy.
Okay, thank you.
Archana, I will get out of your way, and maybe I can answer some of these other questions in the
No,
chat.
please go ahead. I mean, if you have the time, we can answer it. Yeah.
Okay, great.
Okay.
Yeah, sure. So understand the ensembles taken at various stages of this approach. You mentioned averaging or marginalizing over different initializations of the parameter of the network. Yeah, so how much of the results here apply to a single instantiation of a trained network? So I think the empirical answer seems to be, well, everything that we've done has been applied to a single instantiation of a trained network so far. So I think quite a lot. And here's maybe a reason to expect something like this to be true, which is that even if you have a single model, it's associated with some local posterior. And so you can study the geometry of that posterior, and that posterior geometry we expect reflects the properties of that one specific model. And so through that connection, you can use this even if you don't care about the population of all the models in the nearby neighborhood. Yeah, I'll share the materials, the slides, this link that I mentioned, maybe some other links as well here, and maybe somewhere else. There's another spot for me to do that.
Yeah, sure. You can also send it over and I can blast it over the emails so then it can get to all the registered folks. Yeah.
Here's a question about the asymptotic limit in data. Yeah, there are claims that we are running out of data. Because let me address that one first. So empirically, this stuff seems to work even in models trained on only hundreds of samples, right? So maybe the low temperature expansion goes out quite far, as we often see in physics. And so maybe I don't think we're quite running out of data, and this is even relevant if we have few samples. But taking into account finite data sets size effects is, I would say, another open question and an interesting thing you could work on. And then there's a question about, he's got a copy of Watanabe's algebraic geometry of the Gray Book. That's the name we conventionally use for the main textbook in SLT. Well, first of all, congratulations. Excellent purchase. Although it is a difficult tome to get through sometimes. A good way to follow along by training small transformers, closed problems, and studying their weight evolution. I think that's a great thing to do. One of the things I recommend is take models trained on simple algorithmic tasks, very small things. Use the developmental interpretability toolkit. Another thing you can try to do is to replicate some of the work in the papers that we've done. Hopefully, all those things are easier to do the second time around than they were the first time.
Awesome. Yeah. If there are more questions, just feel free to add it on the chat. I will still have like a short, very short
Yeah.
logistics. I know it's a
Yeah.
little boring presentation right now, so I'll just give people a little extra
So,
time to add their questions. Yeah.
maybe I can
If that,
say one more thing.
yep.
If you're interested in more singular learning theory, there's a Discord specifically on SLT and AI safety, and that's linked here. So timaeus.co/discord. I'll drop it right here. Maybe I can just drop the. I can. No, I can't do two things at the same time. I can try, but additionally, there's a website where there's some resources linked. You can always message me or email me or send me a DM on Slack if you have any questions. That's it for me.
Okay. Yeah, they said Thursday meetings time, so I wasn't sure if they were asking me. But yeah.
Is that a question for me?
Yeah, Dennis, if you have like a bit more context, you can add that. Yeah. Okay, I'm just gonna share my presentation, and like if like you can stick around for 5 minutes, we can just let a couple more questions come in while I share it.
Yeah.
Yeah. Okay. Okay, so yeah, again, like I'm just running through the logistics really quickly and telling you about what is to come this weekend. And yeah, so there's a schedule for the weekend, which is also there on the website. It has today's keynote, and then in like around 12 minutes, we have a virtual mixer. So in case you haven't found a team yet, you can come talk to other people, and we'll just have like a round of introductions and see if people already have projects, if they have ideas, and you can form teammates through this. And then Saturday, we have Hack Talks tomorrow. And then we also have office hours. So please do join the office hours because we'll have people around in case you have questions. And then there is office hours on Sunday. And then we have a submission deadline, which is Sunday night or like Monday morning, 3 a.m. UTC. And afterwards, like the submissions will be evaluated and we'll have project presentations on Thursday. And yeah, so the goal for the weekend is to develop like a physics informed framework for AI safety research and use the template under the guidelines. There's a project track, an exploration track, and guidelines is a tab on the website. And yeah, joins in teams of 1 to 5. We usually ask people to join 4 to 5 because then you can get people of different skill sets together. And some of you might have a physics background, some of you might have a AI safety background, and it's great to find people with complementary backgrounds. And yeah, all of our events follow a strict code of conduct. And we have actually in person locations in Singapore, Cape Town, Moscow, and Toronto. And if you have any questions, feel free to write it in help desk. We also have our area chairs monitoring it. And we do monthly hackathons on research to solve core AI safety challenges. And we have done like a lot of previous challenges as well. And you can check it out on the sprints page. And we are a nonprofit project. And just to remind everyone, we actually have two area chairs for this particular challenge, and they have put up a lot of work and a lot of hard work behind this, putting together all the problem statements, making sure you have all the resources. So if they're around, do give them a shout out. It's Lauren and Ari, and they'll be around on Discord as well over the weekend, helping you folks out. So feel free to ask them questions. And yeah, they're the people who came up with the idea behind it. So yeah, they'll have the best answers and the best ways to route you. And yeah, for prizes and judging, we have around like 4 prizes. And also we have great speakers and collaborators who will be judging. Uh, you will submit it on Monday, and from Monday to Wednesday, we'll have people judging. And yeah, you can check out our sprints page and all our monthly sprints that are happening. And we have over 3,000 global participants, now almost 3.5 to 4K. And we do hackathons both in person, but as well as online. And we always have like live mentorship for everyone. And yeah, we're a global AI safety research community. And yeah, remember to have fun. I know a lot of you are extremely technical and extremely driven this weekend, but yeah, do remember to have fun. And yeah, you'll get a chance to sort of learn and develop your ideas with like concrete experiments. And if you have all-nighters, make sure you are well hydrated and take rest as well, because I know it will be very intense. And yeah, if you have some ideas, feel free to go through that, or like put in your ideas on project/teams channel. You can find it on Discord, and you usually find like a list of ideas. Avoid duplicating the ideas, but you can find other people who are looking for like collaborators, or you can look for collaborators. And if someone put up a tag like steal my idea, then you can also go ahead, take it and run with that. And yeah, I think a bit of question answer was also answered by Jesse, but yeah, let's go. I'm gonna stop presenting. Okay, I think, are there a couple more questions for you?
I don't think so. I also just added the link to the SLT Discord if you're not in there.
Okay, awesome.
And I'll
Yeah,
post
thanks
this as
again,
well.
Jesse. I think people were really, really excited. I saw more people coming in all throughout the presentation, so this was definitely very engaging. And yeah, thank you so much for starting
Thank you
this.
guys. Yeah, I guess I'm just going to have to find the time to give a longer version of this talk at some point.
Yeah, absolutely.
Yeah, thank you everybody. Thank you for the organizers. I'm excited. Yeah, and if you do have any SLT questions, just ping me.
Yeah, awesome.
Good luck.
Thank you so much, Jesse. Bye bye.